from Nanjing University of Science and Technology. I'm the chair of this plenary session. The second plenary talk will be given by Professor Richard Leach from University of Nottingham. I will briefly introduce Professor Leach. He has been researching and lecturing on surface metrology for over 13 years. He is currently on the Council of the European Society of Precision Engineering and Nanotechnology, the Board of American Society of Precision Engineering, and several international standard committees. He is the European editor-in-chief for precision engineering and has over 500 publications, including 8 textbooks. He is a fellow of the Institute of Physics, the Institute of Engineering and Technology, Higher Education Authority, the Institute of Measurement and Control, and the International Society of Nanomanufacturing and the International Academy of Production Engineering. The title of his presentation is Trust in Optical 3D Surface Data. Let's welcome Professor Richard Leach.
Okay, thank you very much for the kind introduction and for the invite to speak at this prestigious online conference. It's a shame we can't meet face to face, of course, but that's what's happening these days. So I try to share my screen. This is good. Can you see this?
Yeah, it's good.
Okay, I'll go to full screen then. Okay, so I'm going to talk to you today about trust in optical 3D data. And this is becoming more and more important as manufacturing moves into and society moves into a more data-rich condition. So we're constantly relying on data. So we have to have some kind of trust in that data. And I'll explain my opinions about how we get that trust and then specifically talk about optical 3-dimensional measurements. Okay, so just a little bit about me. I was at the National Physical Laboratory, which is the National Metrology Institute for the UK for 25 years from 1990. I then left and took up a professorship at the University of Nottingham in 2015. I'm also just started in 2018, started a spin-out company to which markets and sells, develops markets and sells 3-dimensional measurement technology, mainly for the additive manufacturing area. And you already mentioned the various boards and councils. Picture there on the right, you can see this is the way to do meetings in the modern world. So we only need to show ourselves from the top so we can wear what we want on the bottom. Okay, so I'm from the University of Nottingham and specifically from the Institute for Advanced Manufacturing. We are perhaps the largest manufacturing group in the UK, significant funding around greater than £80 million worth of funding for manufacturing research, advanced manufacturing research. We've just moved into a new building, which I'll show you in a minute. And we have major industrial stakeholders, primarily from the large aerospace manufacturers, but also from construction, medical devices, and many, many other areas. The main centers in the Institute are Precision Manufacturing Center and the Center for Aerospace Manufacturing, run by Professor Ratchev. The EPSRC Future Composites Manufacturing Hub, which is run by Professor Warrior. The Center for Additive Manufacturing, one of the largest additive manufacturing groups in the world, around 120 researchers there, run by Professor Haig. And the Rolls-Royce University Technology Center in Manufacturing Technology, run by Professor Axinte. I run the manufacturing metrology team, which supports all of these groups. We also have what we call the Smart Industrial Systems Beacon, and this is run by Professor Benford, which is intended to try to link up the computer science people with the manufacturing people, which is very important these days. We have 3 spin-outs in the Institute at the moment in manufacturing. There's Added Scientific with Professor Haig again, TextureJet from Professor Clare, and I've just spun out Metrology. Okay, we've been recently lucky enough to get some significant funding, multi-million-pound funding for what we call the Midlands Centre for Data-Driven Metrology. Midlands because we're in the middle of the UK. That started on the 1st of October. It's a multi-site centre. It's a collaboration between Nottingham, I'm leading it, Coventry and Loughborough, and it's designed to try to take the concepts of data and industry 4.0 and get them out into the UK industrial companies in the region, and then perhaps spread to across the country later on. And we have major input from partners from the National Physical Laboratory, what's called the Catapult Centres, which are specific centres set up in the UK to take academic research out into industry, and multiple manufacturing companies, system providers and trade associations. There's just a picture part of our new building, which we've just moved into, or we moved into relatively recently, but of course we don't seem to spend as much time as we should there at the moment due to the current situation. That's my team, the manufacturing metrology team, established 2015, around 30 to 40 members, depending on how you count, focused on the development of instrumentation and data analysis methods for manufacturing metrology. And we mainly focus on precision manufacturing, and we've done a lot of work recently on additive manufacturing. Okay, so just a couple of words. I guess everyone knows what metrology is, but let's just remind ourselves. So metrology is the science and application of measurement. And one of the main things we can get from a manufacturing context, one of the main things we can get from knowing that our measurements are accurate. So first of all, from measuring what we're producing or how we're producing it, and then having trust in those measurement data, and that all comes about via metrology. So, so it really is a key underpinning concept in the new data world. So digital manufacturing, some people call it Industry 4.0, the fourth industrial revolution, and other names. It's really the application of digital information to enhance all aspects of manufacturing, from the product itself, the processes, the supply chains, the services, even the people management and human aspects. So it's predicted by most countries now to be the future of manufacturing. It allows what we call bespoke mass manufacture. So as rather than making millions of the same part, we can make millions of a part, but all slightly different so that they're bespoke for a given person, application, or whatever. And so that allows us to do things more efficiently, more sustainable, and more cost-effective ways. Okay, so what's the problem? Well, one of the problems is that we produce vast amounts of data when we're looking at digital manufacturing paradigms. And having trust in that data is absolutely critical to all stages of the product use, not just in the manufacture, but also in use as well. So we need to somehow get confidence in data, and that comes from metrology. The concept of traceability, which I'm going to talk a fair bit about, the concept of traceability assures that we can have trust in that data. Okay, so what is this concept of traceability? I hope most of you have already heard of this, but let's remind ourselves. So this is from this definition is from what's called the vocabulary of metrology, the VIM, which you can download for free from the internet, and it gives us all the terms and definitions that we should be using in metrology. So we're using the same language. So I would recommend everyone to have a copy of this. So traceability is the property of the result of a measurement or the value of a standard, whereby it can be related to stated references, usually national or international standards, for an unbroken chain of comparisons. Now, so it's all the calibration steps that eventually lead us up to a national standard, and typically that national standard would be the meter, or the definition. So the meter, and that would feed through an unbroken chain of comparisons to the actual measurements we're doing in industry. And notice this really important concept here at the bottom in red, all having stated uncertainties. We cannot claim traceability if we don't quote uncertainties. And the reason for that is that we can't actually compare two properties or two measurements unless we understand the variability in those measurements. If we have huge amount of variability, we just can't compare them. So unless we state uncertainty, a measurement result is just not enough on its own. We have to state the uncertainty. But this is rarely done. Almost never do I see point cloud measurements, texture parameter measurements, and surface measurements that have their associated uncertainties included. So just a little bit more on what measurement uncertainty is. So every measurement has some uncertainty. There's always some error sources in a measurement. So there is no such thing as a true value. There is always some error. The measurement result is incomplete without some kind of statement of uncertainty. I've already stated that. When you know the uncertainty in a measurement, then you can start to judge whether it's fit for purpose. Have that trust and confidence which allows us to do tolerancing and things like that in manufacturing. And understanding measurement uncertainty is the first step to allow us to then look at what the sources of uncertainty are and reduce them. Right, I have to give you some definitions quickly because I'm going to use these throughout the talk. So please bear these in mind when I'm talking about different types of surface. So the first one is surface topography. What do I mean by surface topography? Well, that's everything. So if I've got an object and I'm trying to measure the surface of that object, everything on that surface, that's topography, what we're going to define as topography. Other people may have different definitions, but for this talk, and as far as I'm concerned, surface topography is the whole thing. Then we have the overall shape of the part. So the low spatial frequency components of the object. And for that, we usually call that form. So that's the sort of thing that coordinate measuring machines measure and things like that. Then when we remove the form from the topography, what remains is the texture. So the texture is the geometrical irregularities present on the surface, and but not including form. So we start off with topography. That's everything on our object. We could extract form, and then we can extract or remove the form, and that gives us the texture. Okay, just another couple of definitions. Sorry, as a metrologist, we're a little bit obsessed with our definitions, but it is important that we're talking about the same things. So first one is calibration, what we mean by that. Now there is this definition, which I'm not going to read, which is from the Vim again. I think it's way too complicated, and I say it's just the comparison between two measurements, one of which is a reference standard or value, the other which is one being tested. In other words, to calibrate something is to check it or compare it against something which is more accurate. But importantly, I haven't included that here, but it's in the main one. You need uncertainties to be able to do that comparison process. Adjustment is often confused with calibration. Adjustment is the set of operations carried out on a measuring system so that it provides prescribed indications. In other words, what we do here is we may calibrate our object, then we use that information to adjust the instrument back to what it should be measuring. So it could be a software correction, or it could be a hardware correction adjustment to the object. So often that's called adjustment is called correction, but adjustment and calibration are completely different. Verification is really the formal definition is provision of objective evidence that a given item fulfills specific requirements. In other words, you are testing to see whether it conforms with its specifications. Now, often that requires uncertainty, but it doesn't formally require uncertainty. So again, calibration, adjustment, verifications are very different things. We need to be careful when what we're talking about when we discuss them. And then the last one, when I talk about a CMS, I'm talking about a coordinate measuring system. And that was the term that was chosen by the International Standards Organization, so that we're not just talking about CMMs, because they're typically the contact systems, but we can also include optical and X-ray systems in there as well. So a coordinate measuring system is something that measures the coordinates of an object. Okay, let's get to the introduction. So, surfaces of modern products, highly complex features. We see lots of freeform objects. We see lots of different types of complex deterministic and stochastic textures. We have very high tolerances and very high slope angles, which often cause problems for the optical instruments. So the range of products in modern manufacturing has got increasingly more complex over the years. And then it all of a sudden took a quantum leap in complexity because along came additive manufacturing. And when that came along, nothing changed. These are still objects. They're still things that we need to measure. There's nothing strange about additive manufacturing, but the level of complexity, and you can see some of the freeform types of objects that are produced, the level of complexity ramped up significantly. And this has caused major problems for the measurements, the existing measurement systems. So in many cases, we have to develop new measurement systems. So we've got lots of freeform surfaces, hollow structures, lattice type structures, and things like that. So very difficult to measure. And often the surfaces are extremely complex as well, not the surface texture. So how do we measure these components? So we're primarily talking about form now. So how do I measure the shape of those components so I can have some kind of quality control in my manufacturing process? Well, the most used technique in manufacturing is the contact coordinate measuring machine. Now, I'm going to assume you know roughly how that works. It's basically we contact the part and then we measure the coordinates from the machine. So it's the most used, benefits from a standards infrastructure that's in place. I'll talk a little bit about that. It's very simple to model. And this is a key point. We can model what happens when a probe contacts a surface, a spherical probe, very hard, contacts a surface. We can model that morphological operation. The probe does not allow access to highly complex. So this is some of the limitations. Because of the shape and size of the probe, it does not allow access to highly complex features. Also, and this is a key limitation, it can take many hours to build up a high density point cloud because we have to scan a mechanical probe across the object. So along came many different types of optical measurements. Now, one key thing about the optical measurements is that they can be much faster. We can take a whole field of data in one hit. So they can be much faster. If we're scanning, they're still slow. But if we can take full field measurements, then they can be much faster and give us millions of points on the surface rather than a few hundred. They do suffer from occlusions and shadowing effects. So if we can't get to the object, so they have some of the limitations of the contact systems. But, and this is the key negative point about the optical systems, is they are very complex to model. And we're going to talk a lot about that today. So how do I calibrate optical coordinate measuring machines? Well, if we do some kind of search for that on the internet, we're likely to come across something like that. There's almost nothing on calibration of optical coordinate measuring machines. Almost nothing out there at all. So many people are using them in industry. They have no idea how to calibrate them. So let's talk about that. So what is the fundamental issue with the optical instruments? So what exactly happens when we take an optical measurement? Well, we have the surface topography. Then we get that scatters the light in our optical measurement, and then we try to record some kind of image. And from that image, we try, or a series of images usually, we try to extract the surface topography. And unfortunately, there's many nonlinear, highly complex mathematical steps that are going on in that process. Often we can linearize a lot of those, and most of the commercial manufacturing instruments assume linearity conditions, but it's not always true. And especially if we have multiple scattering going on, then we have significant problems. So this is why rather than modeling a sphere moving across a surface in some kind of Hertzian interaction, we have to start solving Maxwell's equations, and that's where things get very difficult. So let's just talk about the standards that are in place, or the international standards that are in place for, this is for shape measurement I'm mainly talking about now. So there is nothing on calibration, nothing at all. They're coming because we have some standards on uncertainty analysis, but the ISO 10360 series covers verification, not calibration of coordinate measuring systems. So it's not calibration. It does cover uncertainty. There are some methods for evaluating uncertainty. We can use the budgeting technique, where we take all the uncertainties into account, then propagate them through the measurement model. That's very difficult to do with coordinate measuring systems, and almost impossible to do with optical systems. We can use what's called substitution. I'll talk about that in a minute. Or we can use what's called virtual systems. And they don't exist for optical systems at the moment. So let's look at substitution. Substitution is where we take if we look at the example here in the picture, we've got a sphere being measured. And so we've put a length bar, which is the same diameter as the sphere there, next to that. So we measure the sphere, we measure the length bar, and we can take out some of the systematic effects. And it means that we have a model that we can use to evaluate uncertainty. The problem is if we're using different types of coordinate measuring system, then we have a different probe surface interaction. So here we can see the sphere, the optical interaction, and then this is an X-ray CT type system. So the probe, I put deconvolution in inverted commas because it's rarely a linear process. It's usually non-linear. Even with a stylus probe, it's a non-linear. It's not a deconvolution. It's an erosion process. Especially so when we have rough surfaces like additive surfaces, this becomes a significant problem. And of course, we can only really do this. The examples was with a sphere. We can't do this if we've got that complex freeform lattice type structure. So the other concept to try to get uncertainty is what's called the virtual machine. This is where we have a machine which mimics, it's like a digital twin of the measurement system, and in this case, the example I'm showing here is the modeling the kinematics of a contact coordinate measuring machine, and then we can propagate the error sources through that, usually using a Monte Carlo type approach. So what happens if we look at the virtual systems in the optical world? Well, let's do our internet search again. And there it is. There's almost nothing on virtual machines for optical systems, nothing that can actually be applied to give us realistic uncertainty evaluations. So we're addressing that. Now let's go back to surface texture for a little bit, because we have solved some of the uncertainty issues in surface texture. So I'll tell you what we've been doing in surface texture. So uncertainty budgets in surface texture are very, very difficult. There's so many uncertainty sources that they are extremely difficult to apply. There have been historic attempts over the years to do it, to propagate every error source using it with the stylus instruments. So I worked with a mathematician, Peter Harris, in 2010 to produce an uncertainty evaluation. That's just for the RQ parameter, and it was an 80-page document for one ISO surface texture parameter. Han Heijamer, a good friend of mine, worked on uncertainty in measurement of surface topography and published this in 2015. There's just a snippet of one of his equations he was using, but there is almost nothing published on optical instruments. So what did we develop? So whilst I was at MPL, myself and Claudio Zjuska developed this infrastructure, which is now published as an ISO standard. And we said, well, look, things are too complicated, so let's try and make them a little bit more simple. And I'll show you a picture what is the best way to talk about this concept. So we came up with this concept called the metrological characteristic. So let's talk about that. So here's our measurement model. So this would be a surface measurement in this case. So we have some kind of mathematical model of the measurement, and that could be a parameter measurement, could be a height measurement, could be a lateral measurement or something else. And we've got these influence factors, and there's so many of these. And especially when we start talking about the optical instruments, a lot of these are difficult to determine, and it's just a large number of them with a lot of uncertainty. So we've got to know how to propagate all of those through the measurement model to give us the uncertainty. So with metrological characteristics, we said, look, let's try and define a handful of easily determined parameters that any person in industry can determine. These are fixed values, so we all agree under ISO rules that these are the values we're going to determine. These will encompass all of the influence factors, and we can propagate these through the measurement model as opposed to all the influence factors. So it's a very human thing to do. We're trying to split it down to this small number of components that we can measure. So we did that. It took many years, but we did it. And we came up with these, which are now in ISO 25178 part 600, which is published. Part 700 is still under development, which is how to determine these. So we get these basically cover the scales of the instrument, the amplification, linearity deviations. Then there's the flatness deviation, of course. We're always comparing against a flat plane, usually a flat plane. Then there's the measurement noise, something to do with the resolution of the system. Remember, that's height resolution, not necessarily just the lateral resolution. The XY mapping is the orthogonality between the scales. And then there's this one at the bottom here, topography fidelity, which is the difference between my measurement and a perfect measurement, or a measurement with low uncertainty. That's the one that's not standardized yet, because we still don't know how to do that, especially with optical instruments. So this captures all of the strange effects we get with optical instruments, with multiple scattering, high slope angles, things like that, phase inversions at high slopes, etc. All of those are captured in topographic fidelity. So we're still working on that. This is work in progress. We just published a paper which summarizes all of the work so far on this concept of metrological characteristics, but many industrial companies are starting to embrace this now. So we can do the easy things. We can do the scales, the flatness, the noise, and things like that. They took many years to develop the standard methods, but we can now do them. And you can buy artifacts which will allow you to evaluate those figures. But when it comes to the fidelity, the topography fidelity, then things get more complex. So we need to start thinking about applying very rigorous mathematical techniques to the measurement, to our optical models. So here I'm going to show you an example of what we've been doing with coherent scanning interferometry. So this is a long story. It started in 2008. And I've been collaborating with Jeremy Coupland at Loughborough University, and a lot of this work has been done by my colleague Dr. Surong, and who works at Nottingham at the moment. And we've been developing a three-dimensional imaging model for coherent scanning interferometry. And we base it on, I don't want to go into the details, it's a whole talk in itself. But we developed what we call the foil model, which is we model an infinitely thin surface layer on the surface, and that allows us to linearize some of the processes and define what we call the surface transfer function. And this is not necessarily the same as the optical transfer function, because we're talking about getting topography from optical data. And that's not always a linear process, but we've done a lot of work on this recently. We've also, it allows you, once you have a model, you can start doing adjustment processes. So you can take out some of the odd effects you get when you're measuring high slope angles and small spatial frequencies. You can apply a correction which allows you to take some of those problems out. But more to the point, it gives you, for this talk, it gives you a calibration, which allows you to start thinking about setting up a virtual CSI. So we're just publishing on this now. This is new work. We've basically set up a physics-based coherent scanning interferometer, which is effectively the digital twin or the virtual instrument for CSI. considers all the major influence factors, and we simulate the measurement using a combination of models. But the key point here is that we had to have that three-dimensional imaging model. We have to know that the simulation is highly rigorous, that it's accurate, that it is simulating what's happening in reality. And of course, we have to do a lot of experimental tests to make sure that's the case. So once we have this model, first of all, we can set up virtual model of uncertainty, but also importantly is that we can find that topography fidelity input into the metrological characteristics model. Here's just some results using that. We use the a priori information to feed through the model, the virtual model. We then look at all the influence factors, propagate those through the model, and it allows us to get a very, very, we're very pleased with these results, which are just under review at the moment. So I say I put JOSA, but it might not be. They might not accept the paper, of course. But we can get a comparison with contact measurements or the nominal, and we can also look at the 2 sigma variation. And these effects you're seeing here, we see all of these in experiment, and they are all effects of slope angles of the finite transfer function of the instrument. Okay, that theory only applies if we don't have multiple scattering. If we have multiple scattering, then things get much more complex very fast, and we have to start looking at rigorous approaches to Maxwell's equations. I've been again working with our colleagues at Loughborough University. We've been developing a boundary element solver, which allows us to set up a rigorous virtual model, but this is still work in progress. Okay, let's go back to so that was what we've done and what we're doing with texture. Let's go back to form. So there are issues with the metrological characteristics. Some of those issues are that some of them, and MCs is metrological characteristics, not Monte Carlo. So MCs for texture are object dependent, which means that I can't determine those values independent of the object I'm measuring. Now that would be the nicest situation, is that I can just determine all of these as specifications of the instrument and then just propagate those through whatever the measurement model is. But that's not always the case, because in some cases, for example, with the noise will change depending on the slope angles or the spatial frequency distribution of the surface and height distribution of the surface. And it's quite a big change, so you can't ignore it. So we have to use the object itself as part of the uncertainty analysis. And this is also true not just for noise, but also for the topography fidelity as well. So it's expected that for form measurement, that this issue will be even more pronounced. It's a problem with texture, but remember with texture, often we can assume that the overall form is flat. So that takes out a lot of effects which can cause problems. So the fidelity metrological characteristics will be critical for complex objects. So the other problem is of course, how do we untangle the random and systematic contributions to a form measurement? That's a difficult thing to do. So what we've been doing recently for form measurement is developing this statistical model approach to point cloud positional uncertainty. So this is fully taking into account all of the correlations across the surface. And whenever you use an optical system, all your points are correlated because of the finite point spread function of the instrument, let alone any filtering you might do. So we have to have some kind of spatially variant statistical model. So we've been developing this Gaussian random fields approach to try to model the uncertainty. And the way we get the data is by repeat measurements. So you have to take repeat measurements and then you can model that. If you just model that as a standard deviation, it will be way higher than, or in some cases even lower, but not realistic of the measurement process, because you're not taking any correlation into account. So we model this Gaussian random field. I'm going to go straight to a picture of that, I think. So it gives us a spatial uncertainty map. So here we're modeling a certain spatial distribution of points. We can also go to a larger distribution of points, long-range spatial dependency. And again, we model that as a random field. So this is what you would get. You take your initial probability space. So this is what we would get if we just took standard deviations at each point. We then apply the Gaussian random field in effectively a machine learned process, supervised machine learning process, and that then gives us the new probability or the new uncertainty. We can call this uncertainty now, probability space for that particular point cloud. So this is very new. We're still working on the mathematics behind this, and there is a significant part still missing, which I'll talk about in a minute. Here's just some results. This is a paper which is under review, although I'm pretty sure it will be published because it's at the last stage of review at the moment, which describes this mathematical or statistical model of the surfaces. And we've measured a number of examples, and we can now put uncertainty point on the point cloud. We can put an uncertainty distribution. But there's still some significant remaining issues with this approach, which many of you have probably already thought of, and that's that it doesn't take into account systematic effects. And when we're measuring form with optical systems, we have a lot of systematic effects. There's distortion in the measurements and gamma effects and all sorts of things. So we still need to find the systematic errors. Now, this is an open question. We have some ideas, and we have a PhD student just started, but we're still working on this. So it can be done by maybe taking lots of measurements of different objects and then using Kriging type approaches, something like that. Or perhaps the best approach is to establish virtual optical instruments. Then we can find the object dependent errors and the topography fidelity type problems. So we have been setting up virtual instruments for photogrammetry. For fringe projection, we have students just finished on photogrammetry. We have a current student at the moment who's working on this. And of course, I've already shown you that we can do this for coherent scanning interferometry. But there's all sorts of technical reasons that make it very tricky for these larger measurement area systems, and not just tricky from a physics point of view, tricky from a computational point of view. Okay, so I'm approaching my my time, I think, so I can start to summarize. So we now have several potential routes, and these the routes towards that give us uncertainty for these types of measurement. When it's not finished, we still have some way to go. I predict we've got at least another 5 years or so, if not more, to be able to see people actually giving results. So you can see a production line, and you can see someone on that production line who's got their optical measurement system, and it's not just giving them a point cloud, it's giving them a point cloud with the uncertainty shown on that point cloud. And then it's giving them a parameter that they extract from that point cloud, the diameter of a sphere, the height of the step, and it's giving that with some kind of uncertainty evaluation that's associated with it. That's the sort of the dream for the future. So the metrological characteristics approach can be done in chunks. We don't have to do it all at once. With the ISO standard 25178 part 600 that we've developed for surface texture, we've standardized what we can do, and for now we've left it open the topography fidelity, which is part of that standards infrastructure that we still don't need to do some work. And we can do the same with form. Although we still don't really know what the metrological characteristics should be for form. They'll be similar to texture. The virtual approaches can also come along in chunks. So we can have the relatively simple linear models. So we could have simple models just based on simple Fourier optics. Then we might move to the more complex models using the foil approach, our approach. And then we might eventually end up with approaches which use rigorous methods. But you have significant problems with computational time as you move in that direction. So we can do the very relatively simple models. We can crunch that data in less than seconds. When we get to the foil model, we're into minutes of computation. If we start trying to do these things with rigorous models without having dedicated hardware platforms, then we come into hours or days of computation time to measure that. That's never going to be acceptable in an industrial context. The statistical geometry framework is being developed, but again suffers from computational issues. It's where the Gaussian Gaussian random field process is highly computationally. So we're taking millions of data points. Then we're doing a lot of number crunching, and we need to work out ways to reduce that. Okay, and here's a big question. If we can establish traceability for optical systems, perhaps the next step is not just to establish the traceability for optical systems, but to remove the need for having contact systems as our traceability infrastructure. If we are able to evaluate uncertainty for an optical system using a virtual model or whatever, then we don't need the contact system as part of the traceability infrastructure. If you estimate uncertainty, you are traceable. So if we're able to put our hand on our hearts and have trust in that traceability infrastructure for optical systems, we don't need to go back comparing to contact systems. But everyone does. I do. I always compare. All my students, every paper I have reviewed, always there is the comment, have they compared against a contact system? And even the contact system, often they don't consider the traceability for the contact system, but it's just something we trust. We has the infrastructure in place, and we've been doing this for many years. So people trust it, and that trust is extremely important. But really what we should be saying is, look, we have this traceability infrastructure in place. The trust comes from the metrology, not from the years we've built up of trust in the contact systems. So we're getting there, and we're putting the various tools in place. The next steps, we've developed some of the ISO infrastructure for texture measurement. And there are various projects which are running at the moment in Europe, I know for sure, on developing new uncertainty methods for optical coordinate measurement systems, and we're looking at methods which I presented today. Okay, so with that, I'd like to thank the organizers for inviting me, and thank you guys for listening.
Okay, thank you, Professor Richard Leach, for the interesting talk on measurement uncertainty. I think it's very interesting talk because he gives us a very comprehensive talk to show how he treats the measurement uncertainty in a very rigorous and statistical way. Now this session is open for questions. I will check whether we have some question. Okay, from YouTube or Bilibili.
So Richard, I have thanks for the great talk. So
no problem.
This is also something you know, I have been thinking, right? I have been working on this with NIST, US NIST, developing this standard. So look like the US is way behind Europe. Is there any kind of way to, like between US and you know, Europe to work together, develop this kind of standard for this optical metrology, you know, generic like optical metrology, not surface texture, geometry, you know, all this together. So
yeah, so there is work going on in the US. So Ted Forberger, I know he's now retired from NIST, but he was leading the optical work in the ISO committee. But he has now moved on from that. He's still in the ISO committee, but he's not leading the optical work anymore. In fact, we don't have a lead at the moment. But I think you are right. There is the US does seem to be a little bit behind Europe in this respect. But I'm running a comparison approach and trying to help the US at the moment. So through my activities in American Society for Precision Engineering. So there is some activity going on there. But and the US are also involved quite heavily in the ISO standards. So there may not be so much research going on in the US in this area, but as long as as long as they trust what we're doing in Europe, then you know that them being involved in the standards means that they'll adopt the standards when they're developed.
Yeah, I was on one of the committee developing the standard for optical system, especially in the robotics field. Right. But it's the progress like very, very slow. We started the process last year, and it's already a year long, and we have not moved anywhere.
No, it is very slow, and I think. Well, I hope I've given you some of the ideas of why it is slow. It's a really complicated problem. It's there's probably some relatively simple things that can be adopted, and that even that metrological characteristics approach has taken 10 years of research to do. It's not a simple problem. I mean, we live in this world where if we were producing components and we didn't check our dimensions, you know, and use uncertainty, no one would accept the component. But then we measure the surface, and no one specifies uncertainty, and people don't care, or they've learned to live that. You know, that's the case. But I work with many big companies who are very worried about adopting the optical systems because and X-ray systems actually because they just don't have trust in the systems.
This is a bigger problem.
But there is a way to address that trust issues. The other way to go, which is more complicated or not more complicated but more time consuming, is to use gauge R&R type approaches, and that's how the companies do it at the moment. So they apply measurement system analysis and gauge R&R type approaches, and that works to an extent for that product with that instrument. But as soon as you start playing something, you've got to go through the whole gauge R&R process once again. So uncertainty, if we can get there, will simplify things a lot.
I would, if without a standard, right? So people will not trust the data. That's right. I mean, even to a certain extent, the standard. It's not necessarily the methods that are applied in the standard. It's the fact that someone says, I have applied, they have a stamp which says they've used that standard. Like certified.
And that's enough to show that, that they've complied with, some rigorous tools that give you the right data. But there's a question in the chat box. Should I read that or? So someone has said,
there's new trends that you can read it. Okay,
no problem. There is a new trend that an increasing number of AI or computational methods, good question, are applied in optical sensing, especially 3D data acquisition. How do we build an intelligent but trustful instrument? Very good question. Very, very good question. So at the moment, clearly what we're trying to do is model the physics of the instrument. So we're trying to set it up as a deterministic model that allows us to propagate the various error sources through that model to give us uncertainty. What happens if we have no idea how we got the answer? So if we start using a machine learning type process to give us the answer, it's not clear how we would then propagate the error. Now, some people say it's very simple. You just propagate the error through that new model, through the machine learned model. But I don't think it's completely clear how we do that just now. The other problem with using machine learned approaches, and in my own research, we do a lot of work in this. It's definitely the way forward. But the other approach is maybe not to necessarily understand uncertainty, but to understand the validity regime of your machine learning process. So when does it go wrong? When is it not giving us the answers we would expect? But these are unanswered questions at the moment. There definitely needs to be more research in this area. So it's a good question. I don't have an answer to it at the moment.
Okay, we still have some time. So any other questions from audience or from some other platforms?
In many cases, I can say in many cases with the machine learning processes that are being applied, for example, for phase to height determination, for phase unwrapping, for scatterometry type approaches and things like that. In many cases, the other problem is how to build up enough training data as well to do that properly, and how to know whether you've used enough training data. But these are things we can talk to the computer scientists about.
Yeah, but the important question is, because we have used machine learning to derive the data for the measurements instead of just actually it's a quantitative measurement method, but the deep learning approach, actually the data is from the training data set. This means some prior information.
Yeah.
But for the measurement, actually it's independent from the previous data. So I'm not sure whether the previous data can be directly applied to the actual measurement, because indeed we see a lot of very promising results that use deep learning to give you very nice, for example, 3D profile phase measurement, but we cannot make sure that the data is reliable. I think this may be some problem.
No, it's a difficult problem. So the computer science, if you talk to the computer scientists, they have a lot of ways to determine confidence in the model and whether they're enough training data. But that's not the question you're answering here. What we're answering is how well does it actually predict reality?
Yes.
So that's an uncertainty question. So yeah, I mean, I have applications in process at the moment that for funding to try to look at this problem. It's a big problem. One thing I will say about this is my opinion on the machine learning type approaches. So they are definitely worth investigating and will be the future. But one thing we need to do as a community of engineers and physicists is we must talk to the computer science community. And often we try to we're trained as engineers, and then we try to become computer scientists, and they've been doing this for 20, 30 years. And often when we take our models to them, they'll laugh at us because they've been doing this for many, many years. So it's really important, if you're developing AI approaches, make sure you have an AI person in your team.
Mm-hmm. Yes, I think currently the deep learning in optical metrology is still in its infancy stage. Actually, in computer science, actually, I think the AI tools has developed very mature, but currently in our community, actually, we use it in a very simple and easy way. So I think there's a lot of things you explore.
Yeah, I mean, the difficulty, actually, the difficulty to engage the computer scientists is that typically they will want to do computer science research. So they want to do something cutting edge, whereas we want them to apply it in applications, and they can't produce papers on applications. So we have to try to convince them that they should work with us.
Okay. So I have one more small questions about I see a picture you have shown in your slides that is a transfer function for coherence scanning microscopy. So it's quite similar to the distribution of the shape is quite similar to the optical transfer function. So can you explain it in more details? This means the measurement certainty is related to the transfer function of the system, or?
Well, no. So the transfer function model is used to model so we go from the light that's scattered from the surface. We capture that data. So we have we're NA filtering that, and that whole process going from there to the optical field that we get as a series of images. That whole process has to be modeled as a 3D transfer function model, not a 2D transfer function model.
Yes.
So we can't just apply the simple optical transfer function. We have to look at a 3D approach. Those 3D approaches, they make it much more complicated, but there are some nice things you can do. For example, if we take a 3D object, then that whole process becomes highly nonlinear. But if we just model, which is what we've developed, if we model that as a infinitely thin foil over the object, then we can linearize that transfer process.
Yeah. Yes.
It's actually based on some work by Colin Shepherd did some work many years ago. We just publishing a paper with him at the moment on all the theory behind this. So it's a very elegant theory, but it only applies if we're within the aperture scattering angles of the microscope.
Yes. So I think there need to be some basic assumption to linearize this problem, because actually it's a nonlinear process for image form.
They do. Yeah, you're correct. So the assumptions we apply are that it's our Kirchhoff scattering, which allows us to work within the Born approximation.
Yes, it's weak scattering, something like
weak
this.
scattering. Yeah.
Yes. Okay, I think almost. The time is we should move to the next talk. So thanks Professor Leach again for the
and thank you all for listening and for questions.
Okay, now I will pass my chairperson to Professor Han Bing and Professor Wang Hongbo for the result keynote session.
Okay. Seems there is a connection problem. Dr. Heist, can you hear me?
Yes, I can hear you now. I'm so sorry.
I'm sorry, I'm having a very bad connection. Okay. And I'm very glad to introduce Dr. Stefan Heist. And he received his diploma and PhD degree in physics from the Friedrich Schiller University, Jena, in 2011 and 2017, respectively. And Jena is a city that is renowned for its optics, and where the Carl Zeiss is originated. And since 2012, he has been with the Imaging and Sensing Department and the Fraunhofer Institute for Applied Optics and Precision Engineering, also in Vienna. And since 2019, he has been leading the 3D sensors group, focusing on the development and improvement of 3D scanning systems. And following is his presentation, but for the audience, please remember to vote if you like this presentation on YouTube or Bilibili. Scan the QR code and vote for your favorite slides. Dr. Heist, it's your time now.
So Dr. Wang, his
yes?
talk is supposed to start at 3:05. So we need to wait a few minutes.
Okay, but maybe we can save a little time for more questions, probably, right?
It depends on who. Maybe someone is come here at 3:05. So I think it probably start on better. Yeah.
Okay. So I like to know if my
Stephen, you can wait a few minutes, and when you start on time.
Sure enough. Maybe I can already share my screen.
Yeah, you can share your screen. You start off.
I'm trying to, but it says that someone else has to end the screen.
Of course.
Right. Yeah, sure. So now you should see the title page of my presentation, if everything works fine. And by the way, concerning some connection problems, I hope everything will work out fine, as I'm unfortunately not in my apartment right now, but in the university hospital. That's why I was not able to join you earlier. Fortunately, it's not Corona related, but yeah, as I said, I hope the connection remains stable, and there's no
so
problem.
So far, the connection is perfect.
Perfect.
This happened. Now it's good. So if you find out any kind of connection issues, you just turn off your video. So we see you now. We see you already. So.
All right. But let's try it like this. Yeah. So, all right. It seems to work. So it's 5 past.
Okay. I think it's the time now, right?
Should we start?
Yeah, you can start. Yeah.
Yeah. So, yeah, please.
So, all right. Then thank you so much for this very nice introduction, and good afternoon and hi everybody, or actually good morning from Jena, Germany. As you now all know, my name is Stefan Heist, and I'm working at the Fraunhofer Institute for Applied Optics and Precision Engineering, IOF. And it's really an honor for me to talk to you about our developments concerning 3D imaging in extraordinary spectral ranges. And as there's only half an hour, I'd say let's directly dive into the topic by first clarifying what I mean by extraordinary spectral ranges. And in this particular case, it's simply the electromagnetic spectrum outside the visible spectral range. That means the ultraviolet towards smaller wavelength and towards larger wavelength, the near and short wave infrared, as well as the mid wave and long wave infrared. Of course, the next question is, why can it be beneficial to use these spectral ranges? Well, what we do is we perform 3D measurements by pattern projection. That means we illuminate the object with a certain sequence of patterns, and 2 cameras observe those deformed patterns. That means the basic requirement is that the object is opaque and that it has a diffusely scattering surface. So glossy surfaces or translucent materials or such transparent objects are either very challenging or even can't be measured. And one potential solution can be to use ultraviolet pattern projection, because on the one hand, scattering increases with decreasing wavelength, and on the other hand, the material can have totally different properties in the ultraviolet. Then, if we want to perform 3D measurements that are not only invisible to the human eye, but also completely eye safe, it's very beneficial to go to the shortwave infrared, especially a wavelength of about 1450 nanometers. And in addition, at this wavelength, we also find a minimum of the terrestrial solar spectrum. And finally, going to the midwave and longwave infrared allows us to exploit completely new interaction mechanisms between light and matter. For example, one can measure such a transparent object like this by imprinting, let's say, heat patterns. But before I go into the detail, let me start with a short recap of our measurement principle. Because instead of the traditional phase-shifted sinusoidal patterns with their spatially and temporally constant offset, amplitude, period length, and their spatially constant phase shift, what we use is, and what we like to call them, aperiodic sinusoidal patterns. That means now all these four parameters are spatially and temporally varying. So in the end, the pattern profiles look like this. And now instead of these traditional phase values, we have to use a different metric, namely the normalized cross correlation, to find our corresponding pixels. That means this correlation coefficient is calculated between the temporal gray value sequence at a pixel in one camera and all the other pixels in the other camera. And the maximum of this normalized cross correlation tells us where the most similar gray value sequence is. And this correspondence can be found with subpixel accuracy by spatial gray value interpolation. In the end, this means that most of our setups consist of two cameras and one projector, which projects a certain sequence of such aperiodic sinusoidal patterns. And then the corresponding point, for example, to this one, is found by detecting the most similar gray value sequence, and we can calculate the 3D coordinates of the object point by a simple triangulation. And by doing this for all camera pixels, we can obtain the complete 3D point cloud. For the pattern projection itself, we use a gobo projector, which we introduced a few years ago, and which simply consists of a light source, then a concentrator which collimates the light, then the gobo itself, which is basically a slide with a certain pattern structure, and some imaging optics. And in order to now project aperiodic sinusoidal fringes, we can simply use such a gobo wheel with aperiodic binary fringes. And generating now varying aperiodic sinusoidal fringes is done by slightly defocusing the gobo wheel and by rotating. And since this rotation is continuous and can be done at potentially very high speeds, we were able to measure extremely fast processes. For example, such car crash tests at a facility of the German car brand Audi, or at even higher frame rate, such airbag explosions. And in general, there are several benefits of our gobo projection-based 3D sensors. For example, we do not need to synchronize projector and cameras. By using high power lamps, we can obtain very high radiant flux and high projection frame rates. And what this talk is going to be about, they are or this principle is almost wavelength independent. That means we can build our sensors with light sources with wavelength outside the visible spectral range. And I want to start with a shortwave infrared, which is particularly useful for the identification of persons. So let's have a quick look on how a person like this guy can identify himself. There are a couple of biometric features that can be used, and probably the most common authentication method is face recognition, especially 3D face recognition, because this allows highly reliable person identification in many different areas. And there are several state-of-the-art sensors which can do this, and most of them are based on projecting a dot pattern, and they operate in a similar spectral range between 830 and 940 nanometers, so in the near infrared, which ensures that the person is not distracted by the pattern illumination, but it does not guarantee that the radiation does not penetrate the various components of the human eye. Because Böttner and Walter investigated the spectral transmittance of the human eye, and their results show that at 940 nanometers, half of the incident radiation hits the retina, and at 850 nanometers, it's even 80%. But as you can see, there is a range where no radiation can be detected already after the aqueous. That means at this spectral range, it's not only irritation-free, but also completely eye-safe. And in addition, if we look at the solar spectrum, especially the terrestrial solar spectrum has a minimum at this wavelength due to the water absorption in the atmosphere. So we can expect a reduced susceptibility of the measurement system to natural ambient light, and that's why we decided to develop a shortwave infrared sensor at this wavelength of 1450 nanometers. The thing is, whereas shortwave infrared cameras with, let's say, moderate resolution and high frame rate are commercially available, we had to rely on a self-built structured light projector based on our Gobor projection principle. So we chose such an LED as a light source, which consists of 60 single chips. And if we operate this LED at a slight overcurrent, we can obtain a radiant flux of a little bit more than 70 milliwatts. And the spatial distribution looks like this. That means the LED emits in a pretty large angular space. But for our Gobor projection, the wheel should be illuminated as homogeneously and bright as possible. And this can be done by using a light funnel, which can simply consist of 4 plane mirrors. So in the end, after simulating different designs, we came up with this one, which is kind of a compromise between cost and performance. And then our Gobor wheel with radial aperiodic binary fringes needs to be imaged into the measurement volume by an objective lens. And we also had to design this objective lens by ourselves, and it simply consists of 3 lenses and 1 iris. In the end, the complete shortwave infrared 3D sensor consists of these 2 cameras and our Gobor projector. And since the patterns are invisible for not only for the human eye, but also for conventional color cameras, we can install an additional RGB camera to map the color texture of the face onto the 3D model. And so in this way, we were able to measure several of our colleagues and not only of our European colleagues with their pale skin, but also of Asian, Latin American, and Indian ethnicity. And as you can see, all of them could be reconstructed very well. And most importantly, those are the corresponding shortwave camera images, all of them with the same color scale. And that means that the sensor operates independently of both skin color and hair color. Yeah. And after showing you this, I think a very nice result, it's time to go on and tell you why it's worthwhile to go even deeper into the infrared range, namely mid-wave and long-wave infrared. Because let's imagine we want to measure reflective surfaces or such a transparent object, which is not possible using conventional pattern projection in the visible spectral range, because the projected pattern cannot be observed by the cameras. That's why typically such uncooperative objects are coded to be diffusely reflective, which is time-consuming and may even destroy the surface. And our solution is now to go into the mid-wave and long-wave infrared to take advantage of completely new or different optical and material properties. And the basic idea is to project a thermal aperiodic fringe pattern in the long-wave infrared. And this pattern is now re-emitted and observed by two mid-wave infrared cameras. This is done n times with varying heat patterns. And this results in two image stacks in both cameras, and the subsequent processing and 3D reconstruction can then be done as usual. In the lab, our sensor setup looks like this, with a CO2 laser as a light source. That means a projection wavelength of 10.6 microns and a metal gobo mask, which you can see here. And this setup enables us to project such an aperiodic heat pattern for a short period of time. Then the laser is turned off and the mid-wave infrared cameras observe a certain temperature distribution, which is re-emitted by the surface. And as I said, this is repeated several times. And if we choose our parameters carefully, in the end, the surface is slightly warmer, but the cooling period between each of the projections is long enough to have a sufficient fringe modulation, so we can really see the single fringes in each of the image. Fortunately, this does not only work in such a simulation, but also in reality. Here are some exemplary measurements of a glass flaken or such plastic traces, or of such a glass bottle, where you can clearly see even these imprints in the 3D reconstruction. And last but not least, here's the measurement of polymer glasses with an acetate frame. But although I think that these results are pretty impressive, we were, of course, looking for ways to optimize our measurement method, as there are two main aspects that limit the measurement quality, which is strongly dependent on the temperature contrast. At first, heat diffusion counteracts the temperature contrast generation. That means even very long irradiation periods do not result in arbitrarily high temperature contrast. And secondly, of course, we lose half of our irradiance at the metal gobo. And that's why we came up with a new idea, which is to sequentially project single fringes instead of an entire fringe image. And in this way, we can choose much shorter irradiation periods so that, at least according to simulations, the total measurement time is reduced, even though we have to take more camera images. And in addition, also according to the simulations, the 3D result quality should also be improved. And in order to experimentally verify these theoretical results, we modified our multi-fringe setup by using now 2 cylindrical lenses and a galvanometer scanner. So in the end, our lab setup is kind of simplified and looks like this. And using this setup, we performed several measurements, for example, of this glass honey jar. So this is the slow motion of the camera, real camera images, and the corresponding profile of the temperature difference. And by now taking 120 images within only 1.2 seconds, we obtained this depth map and this 3D surface model. And the massive improvement can be seen when we directly compare the multi-fringe and sequential fringe projection. And I have to stress, please note the different time intervals of both measurements in the upper left corners, because the multi-fringe projection takes about 20 times longer, even though we only used 10 images for the correlation instead of 120. Nevertheless, the 3D result looks worse than that of the single fringe projection method. Of course, we can improve the measurement result quality by taking more images, for example, 30 images, but then the total measurement time is 68 seconds, so more than a minute. And in contrast to that, when we use 500 sequentially projected fringes, we obtain this, I think, really remarkable result within only 5 seconds. Here are a few other measurement results of a plastic gear wheel, some plastic glasses again, such a glass flaken with its metal-coated cap, and of this glass yogurt jar, where we merged 18 views to obtain this 360-degree model. And with these pretty nice results, I want to come to the conclusion of the talk. So I presented you 2 of our 3D sensors operating in extraordinary spectral ranges. At first, our shortwave infrared sensor using a wavelength of 1450 nanometers, which is, as a matter of principle, as eye-safe as possible and comparatively robust against natural ambient light, and which enables us to reconstruct such dense and accurate point clouds with up to 80,000 3D points per measurement. And then I showed you 2 different setups to perform mid-wave and long-wave infrared 3D measurements, which enable us to measure uncooperative objects. And especially when using our new sequential fringe projection approach, we can obtain such high-quality point clouds within very short measurement times. Sure enough, there's, of course, still room for improvement, but given the time, I would rather mention that, of course, all of what I've presented is the result of teamwork. So I want to thank all of my colleagues from the Department Imaging and Sensing of the Fraunhofer IOF. And I want to thank you for your attention, and I'll be happy to answer your questions now. Thanks a lot.
Thank you very much, Dr. Heist. And this is an extremely impressive talk.
Thank you so much.
As an outsider, I have 2 questions. The first question is, I'm like, in my applications, I'm usually frustrated by the measurement of a cut metal surface after mill or after like lathe. So did you try the sequential fringe projection like method on like metal like objects?
Yes, so maybe I can go back to this measurement where we have a metal coated cap, which can be measured pretty well. We didn't go into detail concerning such metal objects because of the properties, especially the absorption and re-emission of metals is totally different than for glasses and other transparent objects. But now that we can project very high irradiance single fringes, it might be possible that this low signal is sufficient enough to still be able to reconstruct. Maybe it now takes not only 1 or 5 seconds, but a minute, but we're kind of certain that it should be possible to even be able to measure metal objects. But this is sure enough.
Even, So even if the heat dissipates faster than plastics, it is still possible to recover this 3D.
That's our hope. We haven't gotten into detail, but yeah, that's something for the future to investigate. But because of, as I said, the higher irradiance compared to the multi-fringe projection setup, the lower signal and maybe increasing the integrating time of the infrared cameras should be sufficient to still be able to reconstruct the surface model.
Well, this will be extremely useful in the mechanical engineering, especially in the machining process. And
absolutely,
that was my first question. And my second question is about the global view. So is it the only option for modulation of light? So are there any other options like surface or two-dimensional patterns?
So we have already...
is one dimension, right? A global view is one-dimensional modulation, right?
I mean, you can. It depends on the structure you apply on the wheel. Of course, you can also, like in our first infrared setup, we used a translational stage because it's not fast enough. We don't need a continuously rotating wheel. And you can apply the structure you want onto this translational stage. But we also have setups, for example, where we used freeform mirrors, where you can also a freeform mirror, or you can, depending on the material you use and whether it's transparent at 10.6 micron or not, you can use freeform optics in general to design the pattern you want to project. So yes, it is possible to project not only fringes or aperiodic fringes, you can also, at least to some, within some limits, you can project all the patterns you want.
Well, thank you very much.
Because you just need a slide. It's like a slide projector at the end.
Yeah. And that were my question. And from the audience, the audience posted two questions. One question is, what's the advantage of this method over PMD? I don't know what's PMD. It's like related with phase.
Actually, I'm also not that familiar with the details.
Yeah, I think it's probably the phase.
Is it PM?
Profilometry deflectometry.
Sorry?
The deflectometry.
Phase measuring deflectometry. Yeah. The thing is, of course, we also have deflectometry systems in our institute, but if you think of such a class object, there's a certain amount, a small amount, I have to admit, but a certain amount goes through the material to the backside of the object and is reflected back and can disturb your signal. So there are, I know, several algorithms to calculate this disturbing signal and suppress it, but it's quite cumbersome and maybe in some at times even not possible. And that's one advantage. And on the other hand, it's as I said, we are thinking about building a phase measuring or some other kind of deflectometry system in different spectral ranges, where it's also useful to use our global projection principle again.
Okay, so thank you. And the second question is about the cost. I guess that you have presented at least 3 or 4, I think you have 3 or 4 prototypes, right?
It depends. I didn't get the first word. Yeah. It's related to?
How about the cost? So the question from the audience is, how about the cost?
The cost, the cost of, I mean,
you have many. So you have many.
Yeah, of course, it depends on the number of sensors you have, but in the end, our global projector is quite simple and consists of only a few parts, and so the projector itself is not expensive. If you look at this infrared setup, depending on the frame rate of your cameras, you end up only for the cameras with let's say up to a 6-digit number in dollars. But if you have if you have lower requirements, for example, concerning the frame rate, you can use low budget cameras and it gets kind of affordable, I'd say, the whole system.
Well, yeah. So it depends on the camera type, right? If you're an infrared with very high resolution and you have much higher cost.
Exactly. But I mean, the hope is that in the future, in several years, they will be much cheaper. It's like in the shortwave infrared, the more applications you have, the more camera types they develop, the cheaper it gets.
Okay, thank you very much for the second question. And there is the third question. Is MWIR, the mid-wave infrared system, sensitive to interreflection, which may occur at reflective corners? So if you're measuring something reflective, so maybe there is an interreflection problem.
Actually, we didn't observe this problem because, I mean, as I said, we first turn on our light source, our laser, which heats up the object. So the surface has a certain temperature distribution. And then both cameras observe only what is re-emitted. So the thing is, you can't observe, it's too small if you have a signal from this only slightly warmed up or heated up surface to be reflected.
Yeah.
You know?
This is for the heating and thermal effects, right? But exactly. What about the modulation one? So using the global view, the first type of the sensors are based on the global view modulation. And the light source is MWIR.
The light source is long wave infrared,
10.6. It's for heating. That's for heating. Yeah, sorry, my mistake. Thank you very much. And any other questions? Okay.
So thanks a lot again.
Thank you very much, Dr.
Yeah, thank you.
Thank you very much. And now we proceed to our next speaker. Our next speaker is Dr. Shi Yifei. And Dr. Shi, are you in the meeting room?
Hello, I'm here. Can you hear me?
Thank you. Yeah. Okay, I'll start the introduction. Dr. Shi Yifei obtained his PhD from National University of Defense Technology, NUDT, in Changsha in 2019. And your advisor is Professor Xu Kai, right? And Dr. Shi was also a visiting student at Princeton University under the advisory of Professor Thomas Frankhaus. Is currently an assistant professor at NUDT. His research interests include computer vision, computer graphics, robotics, object analysis, scene reconstruction, and modeling. And Dr. Shi, it's your time now for presentation.
Okay, let me first share my screen.
Okay.
Can you guys see the video of my screen?
But this presenter's mode.
Oh.
This is presenter's mode.
Let me try to.
Okay, great.
No, not like this. It's wait a moment. What about now? Can you see
wait a sec. Because I'm having a problem with my connection. So at this moment, I can't see your screen. It seems that it's not shared at this moment.
I'm sorry.
So you can have a second try?
Yes.
Okay, it's great.
So what about now? Can you see the screen?
Yeah, now it's okay, but it's not the title page. I can't see the title page. This is a blank page, right?
Okay, what about now? You can see the
okay, yeah, perfect. So this is perfect.
Okay, wonderful. Okay, thanks for the introduction. It's nice to be here. Today I will be talking about our recent work accepted by SIG of Asia this year. This work is about symmetry detection. So in this paper, we focus on solving a long-standing problem that is detecting the symmetries for objects with missing data, such as objects in RGBD images. Okay, so symmetry is here and there in both nature and the synthetic world, and both for 2D and 3D scenario. And symmetry-based analysis is crucial for structural or even semantic analysis of objects, such as shape detection, shape completion, and robot manipulation. And as a precondition of the scene-based analysis, symmetry detection itself is very important. And it has attracted many research attention in both of the computer vision and computer graphics community over the last decades. So basically, symmetry is a purely geometric concept. And the symmetry detection can be solved by purely geometric approaches Previously, one of the most famous 3D symmetry detection method is proposed by Mitchell et al. In 2006. The basic idea of this method is to accumulate local cues of symmetry transformation based on the detected symmetry point correspondences. So once the symmetry correspondences are determined, the symmetry could be induced by simple algorithms such as clustering or voting. And here is another recent symmetry detection method. This method detects symmetries from mesh reconstructed from real-world objects, which is more difficult. But the basic idea of finding symmetry correspondences is similar to the first one. So it can be easily found that the existing approaches for symmetry detection are mainly based on finding the symmetry correspondences, or we call counterparts. There's no chance for symmetry to be detected if there is no symmetry correspondence. And let's consider more complicated scenario. So if only a partial observation of object is given, such as objects in single view RGBD images, can we still detect the object symmetries? So this is actually not that straightforward, because not all the symmetry correspondences can be found in this kind of input data due to the occlusion and the scanning noise. So traditional approaches based on finding symmetry correspondences will not work on such a scenario because no sufficient symmetry correspondences. So we were wondering if there is a learning-based approach to solve this problem. You can collect some data, train a deep neural network, and predict symmetry. Actually, this is a very common storyline for many of the deep learning papers. Actually, we do conducted such a simple experiment trying to solve this problem. We collect some training data from the real world and use a deep neural network that takes a RGBD image as input and outputs the symmetry axis. And not surprisingly, this naive baseline could produce some good results on simple objects, such as chairs, tables, whose geometry is simple and the category is easy to be identified. But however, for novel objects, such as objects with untrained category, we found that this network fails on predicting its symmetry, which indicates that the network lacks of generalization ability. So actually, this very naive learning-based approach is not learning how to predict symmetry. It is learning to perform object classification and post-estimation. So what can we do for that? We have two crucial observations that for conduct this research. The first one is symmetry is a global property, but it is supported by local geometric cues. So if a network could determine the local shape correspondences correctly, then the symmetry parameters itself could be easily obtained. And second one is the searching of local correspondences actually benefits from the global feature. So in order to find the correspondence, both the local feature and the global feature should be involved. Based on these two observations I just mentioned, so in this work, we use a multitask learning strategy to predict not only the symmetry axis, but also the symmetry correspondences using both local and global features. And our method do has other properties. It could detect not one, but multiple symmetries. And it could handle both the reflection symmetry and the rotational symmetry. Last, it is end-to-end trainable. And next, let's take a look at the related work. So if we look back at methods on 3D symmetry detection, there are many. As I mentioned before, most of them are based on finding the symmetry correspondences in the input data. And they can handle objects with missing data. And there are several methods that I would like to mention since they are very relevant to our approach. The first one is the partial symmetry detection proposed by Mitchell et al. So this method is based on matching local point features in pairs and using these matches to accumulate the evidence for symmetries in a transformation space. After that, a clustering stage is used to get the final partial symmetries. And another kind of work is to extract the intrinsic symmetry, intrinsic partial symmetries. So although our method is focused on extrinsic symmetry detection, but it is very interesting to integrate this kind of intrinsic symmetry detection with deep learning, which might be useful for motion captioning or human pose estimation. There's another paper named geometric fitting. So this paper proposed an approach for segmenting the symmetric objects and recovering their symmetries from 3D point clouds. It is purely geometric and no learning has been involved. So now let's take a look at our method. First, I would like to show what is the problem setting. So in order to detect the symmetries, first we need to have a RGB image of a 3D object. So note that the object segmentation is known here to simplify the problem. So in practice, we can segment the object by existing approaches such as a Mazda CNN. And the output are the reflectional and rotational symmetries. So here we need to know that the number of symmetries are not fixed. So the potential approaches need to determine the number of these symmetries and also tell where they are. So this is not a easy task. Okay, next let's take a look at our method. The core of our method is a symmetry prediction network. So we take a RGB image and then depth image as input. The depth image has been transformed to point cloud. And then we use a CNN and a point net to extract features respectively for these two modalities. We then get the point-wise features. So the next step is to get the global feature by using these two kind of features. So we perform a pooling here to get the global feature so that not only the local simple features and the global contextual features have been extracted. And then because we want to predict both the symmetry axis and the correspondences of all the points in the input data. So here we use a point-wise features and make predictions on each point individually. So we first concat the point feature with the global feature. And then for each of the point-wise features, we make a prediction on and to get the symmetries. So for the symmetries, there are two components, symmetry axis and symmetry correspondences or counterparts. And we use a multitask learning to penalize the incorrectness for these two terms. So this is the point-wise symmetry prediction. Okay, next let's take a look at the loss function. So because we are using every point to make individual prediction, so we have a dense point loss. So the total loss is the sum over the loss of all the points prediction. For point-wise loss, it is very simple. The first one is a symmetry type classification loss, which used to tell you whether this symmetry is a reflectional one or a rotational one. And the second one is the loss for symmetry axis and symmetry counterpart. Actually, this loss is different for the reflectional symmetry and rotational symmetry. As for the reflection symmetry, here we consider a current point as Pi. For the network, we will output a point, OI, which is a projection from Pi to the reflectional symmetry plane. If we connect these 2 points, so we can have a normal of this symmetry plane. So OI and NI could represent a reflectional symmetry. But here, what's more important, we also output the counterpart for Pi. So although the counterpart prediction is redundant for our task, but it is very crucial for the network to learn the essential property of symmetries. And we found that it could greatly increase the generalization ability across category of our approach. So the loss function here looks a little complicated, but the simple idea is to consider both the symmetry axis and the symmetry counterparts. So here is loss for rotational symmetry. So we suppose that the current point is Pi, and we also output a point in space OI and a direction Ni. So the OI and Ni could represent the rotational symmetry. And for the counterpart prediction, unlike the reflectional symmetry, the counterpart for rotational symmetry is not 1 point, but many. So here, instead of predicting 1 point, we are predicting a cycle. So the loss is more or less similar. And the next question is, since we don't know the number of ground truth symmetries, we need to handle these multiple symmetry cases. So assume that we have object like this, and we use our network to get the point features. And we will use a module to output multiple symmetries. The output number has been set to M. So the M is the max symmetry number the objects could have in the data set. So we have some redundancy here. And then we have a binary classification. It is used for filter the false positive symmetries so that we could control the output numbers. And then we have the ground truths. Here we have a problem that is, how can we determine the correspondences of the prediction symmetries and the ground truth symmetries? Because if you don't know these correspondences, then you can't back propagate your loss. So here we have a optimal assignment to solve this problem. So please note that all these steps could be used for end-to-end training. So we have just talked about the training step. So for the inference, once we have the pointwise symmetry prediction, then we use a clustering to make the prediction aggregation so that we could get a unified predicted symmetry. Also, we have a visibility-based verification after that, which could increase the precision of the results. Okay, so in order to evaluate the proposed symmetry detection approach, suitable data sets should be used. There are some existing data sets that could use for symmetry detection. However, they are either too small or not realistic. So we built a benchmark by ourselves. The benchmark is based on existing data The data has come from ShapeNet, YCB, and ScanNet. So here, for ShapeNet dataset, we have 3 subsets for the testing. Holdout view, holdout instance, and holdout category. So the holdout instance and holdout category contain RGB images from novel objects that have not been trained on during the training step. So we can evaluate the cross instance or cross category generalization ability of our method. So next, let's take a look at our results. The first one is a chair. As you can see, the chair is heavily occluded. Some of the parts are even totally missing. But our network could still predict the symmetries correctly. Here's another example. It's a larger object. It's a car. And you can see that only a very small proportion of its surface has been observed in these RGB images. But our method could predict it correctly. The next example is the prediction on, I think, novel category object with multiple symmetries. So this object has not been trained during the training step, and our network could produce 2 symmetries that are perpendicular to each other. And also, we have a tested on the case of composite symmetries, such as a chair with a reflectional symmetry on the top and a rotational symmetry at the bottom. And we also compare our method with several baselines. There are 3. The geometric fitting is the state-of-the-art, purely geometric method. And the RGB retrieval is a very simple learning-based baseline that use a global feature vectors only. And for the third one, shape completion, it is a combination of a shape completion network and a conventional symmetry detection. So for the shape completion network, it has some generalization ability on shape completion task. So it is actually a pretty strong baseline. And we use a PR curve to evaluate the results. So where the higher curve means the better results. So let's take a look at the results on ShapeNet. So from left to right is the result on ShapeNet holdout view, holdout instance, and holdout category. And our method outperforms the baselines by a very large margin over all the subsets. And crucially, our method achieves a relatively high performance on the holdout category subsets, the last one, that include very different objects from those present in the training data. Oh, here are some qualitative comparison. So as you can see, here is a chair with only part of it being observed. So for the geometric fitting, because there's no correspondences could be found, so there's no symmetry being detected. And for the RGB retrieval, because its features are too simple, the detected symmetry are not that accurate. And the shape completion and our method could produce the final results correctly. And let's take a look at another example. This is a chair with a more complicated geometry for shape completion results, because it fails on the completion stage. So there's no symmetry being detected for that. And other methods also fail on such a data. We also did some ablation study. There are 3. no RGB input, which means we only input the depth map and no appearance feature is being considered. And another one is no verification. And the last one is no counterpart prediction. So no counterpart prediction degrees the results most. That tells that the counterpart prediction is very crucial for our method, which confirms the intuition presenting at the very beginning of my talk. An interesting observation is that the baseline without RGB input achieves a relatively comparable result to our full method, and even better results on the last one, the holdout category. So this actually demonstrates that to the unknown objects, it requires geometry larger than the appearance, which is a very interesting finding of our research. And for the runtime analysis, our method takes several hours to train on the benchmark, but the inference, the aggregation, and the verification are very fast. And actually, it is dramatically faster compared to any of the previous methods. Okay, since we have this very exciting symmetry detection method, I'm going to show you some of the application by using the predicted symmetries. Unlike previous work that focusing on completing the shape by using the predicted symmetries, we focus on a more unique application. That is to apply our predicted symmetries to aid the 6D pose estimation from single view RGB images. What we do is very simple. For the dense fusion, which is a state-of-the-art 6D pose estimation approach last year, we fit network with a predicted symmetry from our approach and use the actual feature together with the RGB image to predict the 6D pose. So as you can see, our method could increase the accuracy of the pose estimation, and especially for those are symmetric. Another interesting application is symmetry-based segmentation of RGB images. Although we never trained the network on segmentation task, the network could still learn to segment the objects by using the pixel-wise symmetry prediction. And for future work, I think there are several. The first one is, for this work, we are only detecting major symmetries of the objects, but there are still some symmetries of the tiny parts in the objects. So if we could organize all the symmetries are different level of objects, and we will have a better representation of the objects, and we have better feature for this object. This is very important for the geometry processing. And the second one is self-supervised approach. So when we're preparing the symmetry detection network, a lot of efforts have been spent on data labeling. So it is very interesting to explore a self-supervised method. The last one is integrate symmetry prediction into other tasks. So although we have demonstrated that symmetry could aid the 6D pose estimation, introducing symmetry to other tasks is non-trivial. But there are actually two applications that we are working on. The first one is lane detection. So when the self-driving vehicles are moving, it is possible that some of the lane will be occluded by other vehicles, such as the right lane on the right. But those lights are very crucial for the drivers to make decision and control the vehicle. I believe it is possible to use symmetry prior to detect the occluded lanes for self-driving car. And another one is for robot grasping. We realize that when it comes to grasping with 2 fingers for a robot arm, the robot tends to land its 2 fingers on the 2 points opposite to each other with respect to their symmetric plane. So basically, it means that the robot prefer to grasp the symmetric parts on the object. So it is a very interesting direction to combine the symmetry detection with robot grasping. That is all of my talk. The code and data of SymmetryNet are available, so you're welcome to download and run the code. Thank you very much. I'm happy to take the questions.
Thank you very much, Dr. Xu. Thank you very much for your great presentation. At the beginning, I was trying to ask the application and also with other audiences, but you explained it well at the end of your presentation.
Yes.
So at this moment, I don't have any questions with the application, but still I have some questions about the principles of the training. So to detect symmetry, do you need to like train the algorithm with all the possible symmetric objects? For example, like chairs, like cars.
Go ahead.
And can you extend your like algorithm to some objects that it's never seen?
Actually, this is a very good question. We do have some object category that has never been trained on during the training stage. So I've just mentioned about the ScanNet holdout category subset. For the training, we have like 12 categories like chairs, tables, something like that. And then for the testing, we test our method both on the trained objects and the novel objects. So that is a very core of the intuition of our approach.
Oh, thank you. And another thing is about the moving. For example, the non-static object. For example, like human. Human, I think they're like symmetric, but occasionally we can like make ourselves asymmetric. For example, raising one arm, but keeping the other arm down.
Yes.
So is it possible to detect the symmetry in such occasions?
Currently, I would say we can't, because this is intrinsic symmetries, not extrinsic symmetries. But as I just mentioned in the related work, previously
yes.
Hello?
Yes?
Yeah. Previously, I have mentioned that the intrinsic partial symmetry detection approaches. So I think the problem you have just mentioned is for the human. Yeah, partial. Yeah, for the human that is not symmetric in the Euclidean space, but it is symmetric over the surface. Imagine that
you're right. Yes,
yeah.
I see. Thank you very much. Another question from the audience: how to locate symmetrical objects in the picture? So I think this is some technical detail in your previous slides, right?
Yes.
Locate the symmetrical objects in the picture.
Yeah, that is actually a very good question. So in this work, we assume that the segmentation or the detection is given. we are not studying the detection part. So we just use the ground truth segmentation here. Yes.
Okay. I see. Thank you.
Thank you.
Any other questions from the audience? Okay, so this is all the questions. And thank you very much, Dr. Shi. And
thanks for the
let's take a coffee break. And for the next slide, next presentation will begin at like 16:50. So which is like 5 minutes later. And thank you very much for attendance and see you later.
start now?
Yes.
My name is Bing Pan from Beihang University. I'm very pleased to have this opportunity to chair this session. First, it's my great pleasure to introduce the first keynote speaker, Dr.
It's Van der Yacht, Dr. Van der Yacht.
Van der Yacht. Yes, let's first give a brief introduction of Dr. Van der Yacht. He graduated as a master in physics in 2010 and received his degree of PhD in science physics in 2015 at the University of Antwerp for his dissertation entitled Optical Techniques for Real-Time Morphology Measurement of the Tympanic Membrane. His current research he is currently researching new optical methods for measuring human eardrum shape in real time and in vivo as a postdoc fellow in Belgium. Let's welcome. Now it's Dr. Van der Yacht's time.
Hi. So can everyone hear me?
Yes, I can hear.
Oh, great. Okay, so I'll start to share my screen.
Yeah.
So can you see the screen, or should I put it full screen?
Yes, I can see. Very good.
Is it okay like this, or should I put it full screen?
I think full screen is better.
Let me try. Is this better?
Yeah, perfect.
Okay, thanks for the introduction, and thank you for the great organization of the forum, and also thank you to Song for inviting me. My presentation today is about single-shot structured light profilometry using deep learning. So, like my previous speaker, I will also use deep learning to achieve my goals. Let me first introduce a little bit about my background, so where I'm from. At the Laboratory of Biomedical Physics here in Antwerp, we're mostly interested in examining the human tympanic membrane. The tympanic membrane is just a difficult word for the eardrum. So the human eardrum is what we're actually investigating, and we're investigating all kinds of techniques to map the surface morphology of the eardrum. In a couple of slides, I will explain to you why this is so important. And this is the first part of my presentation, but the most important part I'm going to talk about today, since it is an optics forum, is about the way that we want to extract the height information from our microscopic surface using deep learning based profilometry. So let me get straight to the point. What you see here is a classic setup for multi-phase structured light profilometry. I'm sure most of you will be familiar with how this works. You have your object, and you can I point in my presentation? Can you see my mouse right now or not? Can you see the mouse? Or
yes, we can.
Is it not?
Sam.
Okay, great. Sorry. So you have your object, and it has some kind of curvature. And what we do with multi-phase structured light profilometry is we project multiple phase-shifted fringe patterns onto the surface, and we capture it using a CCD camera that is placed under an angle. So this angle is very important. We need at least 3 phase-shifted fringe patterns, but usually standard 4 are used, or even more can be used also, but you need 3 at least. And then you combine those 3 phase-shifted deformed fringe patterns into a phase map. This phase map is actually the surface of your object, limited to the principal domain value of your arctangent function. So you have to add an integer number of 2 pi to each pixel to obtain the unwrapped complete 3D phase map. So this is a technique that is very robust to noise. It works very well, and it has been used for decades to extract height information from an object. So standard, you need 3 or more fringe patterns. What we propose to do in a paper that we published last year in the summer is to train a network to learn directly the link between only one of those input fringe patterns and the output phase map directly. So how we want to do this is we will obtain a large set of input-output data couples, let's say, and we do this using standard multi-shot phase shifting profilometry. So we know that the output image is correct. But then we will limit what the network can see to only one of the 3 input fringe patterns. And we want to establish a link directly. This way we can bypass the other 2 fringe patterns when it is looking at a new fringe pattern that it hasn't seen before, and directly predict what the surface should look like. And as an added bonus, we can also bypass the cumbersome phase unwrapping, which is an algorithm that is prone to cost computationally a lot and is prone to errors sometimes. So in our paper of last year, we provided a proof of principle, and we did this by using simulated images, because as you know, for deep learning, you need a large data set. So what we did was we virtually established some randomly shifting surface maps. We projected a sine wave onto it, and then we looked at it as it is deformed from under an angle, and we store that deformed grid pattern. So first we generate a random height map, then we project our periodic sine wave, just the way that you would do in a real setup, and then we observe it under an angle alpha. In our paper, we use 30 degrees, which is somewhat typical for real setups. Then we store these deformed fringe pattern original height map data couples, and we repeat this process 10,000 or more times. So since this is simulated, you can do this very quickly, and you can generate a database of a couple of 10,000 of those samples in a matter of minutes. So this can be done rather quickly. What you see here is we modulated the degrees of freedom that we gave our random surface, our random surfaces. So it had the opportunity to be moving not so much like in the beginning here, where there's only 1 degree of freedom, but then we gave it also a lot more degrees of freedom. In the final sample here, you can see it is allowed to move up and down 19 times randomly. We also said that they could be interpolated using a spline, so more or less curved, but we also allowed it to have sharp edges. So that's what we actually want to do here is we want to create a large set of eigenvectors, which is capable of mapping the entire 3D space. So when we present our network later with an actual deformed fringe pattern of a real object, that it has all the tools to extract from it the surface map. Next are our network structure. So in the paper we published last year, we used a simple, straightforward, fully convolutional network of 10 layers, and each filter had the opportunity to be about 5 by 5. We experimented with lots of different filter sizes, but we mainly found that 5 by 5 images filters works best for our 128 by 128 input fringe patterns. It could be that for your specific application, you need to monitor these parameters, because before we got the network to actually learn something, we had to fine-tune these hyperparameters a lot. So in the beginning, it didn't learn anything. It wasn't unless we actually got the parameters just right that it started to converge to towards a solution. So it should be noted for people working in deep learning, this may be obvious, but for the others, maybe it isn't. It's very important to notice that the training in which you do forward passes and backward passes, adjusting the coefficients of your matrices in the middle, takes multiple hours. It can even take days. But inference takes only milliseconds. Inference is when you present a network with a new input fringe pattern that it hasn't seen before, and you want to predict directly the output. This can be done in a matter of several milliseconds. So the technique is capable of achieving real-time performance once it is trained. But before that, you have to train it, obviously, and this can take a while. Now, let's have a look at my actual first results. So these are the first results back when I didn't know whether or not it was theoretically possible for a network to extract height information from a single deformed fringe pattern. I didn't know if it was going to work. And in the beginning, it didn't work at all. It didn't learn anything. It wasn't until, like I said, we got the parameters just right that we started to see that the error went down. So this was actually what you see now, the first hope that we had of having the network actually working in deciphering the deformed fringe patterns. So we saw, and I was very happy to see this, that there was some kind of structure in the prediction of our input pattern, which corresponds to what it actually should be. So here in the middle, you see what the input fringe pattern surface shape actually looked like. And in the right, you can see what my network thought it should be. So it's very bad. You couldn't use this in real applications, but still you can see there is some of the logic behind it that it starts to comprehend. So the RMS error was still 40%, was way too bad, but we started fine-tuning the parameters now. And in a couple of days, we got the prediction error to go down, and we got it to go down more. And here it started to look already a lot like what it actually should be. And fine-tuning it some more, we got the root mean square error down to less than 1%. So we obtained theoretical proof of principle by this, that it is possible to link the input fringe pattern directly to the outputs. And this was very promising. So let's have a look at what happens when we present our network with some more input fringe patterns that it hasn't seen before. For example, in the first row, you can see a standard ball. So I just made some 3D surfaces, and then I projected my sine wave patterns onto it and presented this deformed fringe pattern to my network, the same network. And you can see in the second column is what it should be, and the third column is what my network predicts it is, without any other help. And you can see already that the error remains lower than 1% of our entire surface map. So it predicts a perfectly curved ball pretty well, but also, and we were happy about this, it was able to predict, as you can see in the second row, the sharp edges that appeared when we monitored a pyramid. So there is some systematic errors at the lines, but nevertheless, the error for our pyramids with sharp edges remains lower than 0.5%, which is pretty good. And then finally, we presented it with an actual measurement that we took from a mannequin head doll, and it was also able to extract the full face of the mannequin head with an error just above 1%, but it had some pretty tricky face shifting abnormalities near the eyebrows where the reflection wasn't so good. But you can see that the network automatically interpolates where it doesn't have any good information, because, well, the deep learning, the way that the deep learning works is that you use multiple layers of features that are combined into a final solution. So it is able to learn from larger symmetry patterns that are present in the input fringe pattern. So it's not completely lost when there's not good information, for example, near the eyebrows or the nose cavities. So we were very pleased about this. Another interesting property or capability of our network was that it was actually very robust to noisy input images. And this is quite important in optical setups. As you know, there is always the problem of noise. And we wanted to see if we add some Gaussian noise to our input fringe patterns, how was it going to affect the surface shape prediction? And we were happy to see that even if we put up to 1% of variance Gaussian noise, it was still able to predict the surface map within 1%. It wasn't until we really added noise of 10% variance Gaussian noise that the error started to go up exponentially to multiple percents of RMS errors per pixel. Now, even then, you can see that the network is still able to predict the overall surface variation rather well. There is just some added noise to it. So it's not completely lost, but it tends to go down when you add so much noise. Okay, I've arrived at the second part of my talk, which revolves around why do we want to do this? Why do we want to measure in our application, in our lab? Why do we want to use this deep learning technique to measure the eardrum surface shape? And I have to, I'm gonna very briefly introduce you to some of the biology of our middle ear. But this will explain why we want to go through this trouble to develop a technique which is able to reconstruct from a single shot fringe pattern a surface map of a small object. So your tympanic membrane, which is depicted here, it forms the separation between your outer ear canal and your middle ear cavity. So the middle ear cavity is right behind the eardrum. And in a paper of 1994, it was first established that the elasticity of your eardrum, the amount that it deforms or displaces under a given pressure, is directly related to the stage of middle ear inflammation. So it's directly related to the stage of disease, how bad it already is. So the more it is it bends, the more the disease has already manifested. And this was an important discovery done by Bagger-Schobach in 1994, because this allowed ENT doctors, ear, nose, and throat doctors, to quantitatively establish the stage of disease of a human eardrum. And it's very hard to do this unless you actually remove the eardrum and study it, but then the patient doesn't have any eardrum, so it's not a solution. The problem was, in 1994, there wasn't any way to measure the eardrum elasticity without removing the eardrum and applying pressure over it. So what we propose to do now is to measure the surface shape of our eardrum from the outside in real time, and then ask patients to close their nose and to blow, and then the middle ear cavity will be ventilated, and this will cause a change in the surface shape of the eardrum to appear. And by measuring the volumetric displacement in milliliters, we can measure the elasticity of the eardrum. This is one important application. A second important application in ENT surgery is the quantitative establishing of how well your Eustachian tube is functioning. So the Eustachian tube, it forms a canal between your middle ear cavity and the back of your throat. So this performs actually the ventilation of your middle ear cavity. So patients which don't have a properly functioning Eustachian tube are unable to ventilate their middle ear cavity sufficiently well, and have some symptoms such as, for example, a retracted eardrum, or the ossicles here will break, or there's a heightened chance of infection and other kinds of symptoms, all because their Eustachian tube doesn't open and close properly. Now, your Eustachian tube is behind your middle ear system. So if you want to monitor this directly, you can do it with MRI or CT scan because the resolution is too low. So you have to actually cut the patients open and see if the Eustachian tube is obstructed. And this is very invasive and oftentimes leads to unnecessary surgery. So what we propose to do is, again, to measure the surface map of our eardrum and ask patients to clear their middle cavity, again, by closing your nose and blowing, or by swallowing. You automatically open your eustachian tube normally, and you should ventilate this. So we should be able to see a volumetric displacement in our eardrum when patients perform such a clearing maneuver. So we could see if the eustachian tube is functioning, but we can also quantitatively assess how well it is functioning just by assessing how much milliliters is moved by such a clearing maneuver. So this is quite important to surgeons, because they can also establish a quantitative way of how well the surgery works for resolving the problem. And for example, here on the right, you can see they're placing a small balloon inside the eustachian tube to help patients ventilate automatically. Now, how well does it work? Today, doctors are pinned to a questionnaire by the patients that say, well, it's somewhat better, it's a lot better, it's not really better. But this is very, how should I say it? It's not a golden rule. It's not objectively evidence-based. So surgeons need a quantitative way of assessing how well their surgery works. And this could be such a quantitative way of doing so. So what did we do? Well, we injected this technique into a surgical stereo microscope, as you see on the left. A surgical stereo microscope typically has two optical axes, one for each eye of the examiner. This provides the operator with some sort of qualitative 3D perception of what he's looking at. I should say qualitative, and it's not quantitative, because it doesn't have any idea of how deep the different surface variations are. This is just a stereoscopic effect. Okay, so we inject in one of the two optical axes our structured light pattern, and we observe it under the other optical axis as it is deformed by the eardrum shape using a CCD camera. And what you see here on the right is the result of our measurement when we measure the tip of a pen. We were able to obtain a resolution of better than 20 micrometers, which is very much sufficient to measure human eardrums also, as you can see on the bottom. As a second step, we want to miniaturize this entire surgical stereo microscope into a portable handheld device, because stereo surgical microscopes are expensive. There's not many of them. And also it's hard to move them, to orient particularly well into the ear canal onto the patient's eardrum. So another advantage is that we can enlarge the angle between projector and camera as much as we want here, limited only by the speculum which is inserted into the patient's ear canal. This is important because the angle between projection and observation is crucial for the resolution that is obtained using our structured light profilometry. Well, here is again the video of a real human eardrum. This was ex vivo, so this is not on a living patient. This was optically cleared and harvested from a cadaver. But you can see you have some feel for the shape, the tent-like shape of the eardrum. People tend to think the eardrum is two-dimensional, but it's actually very much three-dimensional. And this is also crucial for the proper functioning of your eardrum. So next, what did we do? Well, this harvested middle ear, we applied some dental silicone paste on the entire temporal bone, so that we could seal the middle ear cavity inside completely airtight. So what you see here, the pink is silicone paste to shut the entire back of your temporal bone airtight. And then we placed a small tube inside the middle ear cavity, and we hooked it on to our pressure generator. And when we modify the pressure generator, we observed the eardrum, which was left intact inside here, with our otoscope. And what the result you can see here. So when we moved the pressure inside the middle ear cavity, you can clearly see that it's translated to the eardrum, which is moving as well, and we can quantitatively measure how much it moves. And this was the first proof of principle that structured light profilometry can be used to assess the ventilation of the middle ear cavity for the first time. Here you can see some more graphs of our measurement, which was published in 2017. You can clearly see the blue line here, if we monitor the center part of our eardrum, that it moves concordingly with the pressure generation that we placed inside the middle ear cavity. Okay, so next, what is going on now in my research? Well, first we want to transition into real images. This is quite important. We want to move away from the simulated data set, so we need a large real image data set. And for this, we made this big Ferris wheel with randomly varying surface shape. In the center, it is varying a lot, and towards the edge, it's varying a little less. And this rotates automatically. It takes 3 images of deformed fringe patterns, and it combines them into an output surface map. Next, one of those 3 inputs fringe patterns together with the output 3D map is stored, and we have a data couple. And this is repeated several 10,000 times. If you leave this Ferris wheel to spin for 1 hour, you have about 1,000 images. So if you leave it on for 1 day, then you have a data set which is adequately large enough to train your network with. So we wrote a paper about this, which will appear very soon. We will also make these images and the data couples publicly available, so that beginning researchers can try to establish the network of their own. Also, we're updating the integration of our optical engine into our 3D otoscope into a more ergonomically suited device. So what you see on the left is what happens when you let physicists design a medical device. We just take a metal plate and we place our components onto it, and we're done. But we started to cooperate with the Faculty of Design Sciences to make it more ergonomic and also to make it more optically efficient. So this is what it actually currently looks like, our device. Here on the right, you can see a cross-section. There's a camera, a miniature camera inside. There's a semi-transparent mirror. There's a static fringe pattern, which is illuminated by an LED light source. There's some focusing optics onto it, and here at the end you can see the speculum, which is inserted into the patient's ear. We're also moving away from our fully convolutional standard network and upgrading it to a network architecture which has had more success in the last years, which is the UNet. It's very logical to condense your large input size to a smaller input size of features, and then maximize the amount of training parameters that the network has to learn on that smallest part, since it has the most oversight, and then to decode it again into an output segmentation, an output 3D map, in our case, of an arbitrary size. Next, we're starting clinical trials, but as you know, because of the corona, this has been postponed. So we've only measured on ourselves a little bit, but we're going to start clinical trials for, using our 3D otoscope. And I'm also happy to say that 2 months ago, we received a patent for this device combined with the deep learning technique from the European Patent Office. With this, I can conclude my talk. I want to thank everyone for their attention, and I urge them to find me on ResearchGate if you have more questions. I will gladly answer them also there. and all my papers are open source available over there. So thank you for your attention.
Okay, thank you very much, Dr. Sam. We have time for one question. Are there any questions from the audience?
Yes, I have a question.
Okay.
Yeah, it's a very nice talk. So my question is, as we know, the deep learning based method is a data-driven method. So I think it's a very nice idea to generate the training data. So how to make it close to the real data? I mean,
yeah, this is a This is a very good question, because this is actually the essential part of the network, to have your training data look as similar as possible to what you're actually going to investigate. So this is an area we're working on right now. You can choose to have your network be general, so able to measure any kind of deformation, or you can also go more specific and only train on surface shapes that you know it will more or less look like. So for example, in my case, this could be by only training the network on eardrums. So it will always have some kind of tent-like structure, which will also always be concave. And this way it can't think, for example, it's a squirrel or something. It will always look more or less like your eardrum. So what we're doing now is we're placing a large variety of eardrums in our 3D setup, and then measuring them as we move them using the pressure generator and storing all of those surface maps. But this depends on your application. Yeah.
Yes. In my opinion, I think the angle between the projector and the camera may be a factor that may affect the training process. Do you need to adjust the angle during the generation of the training data?
Well, absolutely. It has to be similar to what you're going to use in the final product, because if you change the angle, the deformation will change also, and the network will think it's something else. So the angle has to be fixed. You have to fix actually what your eventual setup will be, and you have to use the same angle for training. Yeah.
Okay, thank you very much.
Thank you.
Dr. Sam, thank you very much. So due to the time limit, we have to move on to the next talk.
Okay, thank you.
Our next talk will be given by Dr. Xinxin Shao. He is very active in the field of digital image correlation and experimental mechanics. His talk is entitled, the title of his talk is Real-Time 3D Optical Deformation Sensing and its Application in Large Engineering Structures. Okay, Xinxin, welcome.
Okay, thank you for the introduction. Good afternoon, everyone. At first, thanks to the Professor Zhang for the invitation and for the opportunity to give the presentation here. And my name is Xinxin Shao, and I come from the School of Civil Engineering, Southeast University. The title of my presentation is Real-Time 3D Optical Deformation Sensing and its Application in Large Engineering Structures. The presentation can be divided into 4 parts. The first part is the research background. As we all know, the optical deformation measurement is very important in many fields, including civil engineering, mechanical engineering, the material science, and the biomedical engineering, and so on. It is very important. In the field of experimental mechanics, the optical deformation measurement field can be divided into the interferometry measurements and the non-interferometry measurements. For the interferometry measurement, we need to use the laser, and the long interferometry measurement is have some advantages. Easy setup, non-sensitive to vibrations, and it can measure large deformation, and it can have various field of view. The serial digital image correlation, short as serial DIC, is a very famous long interferometry measurement method in the field of experimental mechanics. It's based on the principles of DIC and serial vision. So the principle is very simple, and if we have two cameras, the left camera and the right camera, for before deformation at the time 0, we capture two images. And if we can do the correlation between the left camera image and the right camera image, we can reconstruct the point, 3D coordinates of the point based on the principle of serial vision. And if we can coordinate the same point with the image after deformation, then we can calculate the 3D displacement. And if the point near this point has also been calculated, we can calculate the strain. So the principle is very simple, and so it has been used a lot, especially for engineering applications. Instead of using the natural texture directly, normally we use a speckle pattern for high accuracy deformation measurement to minimize the measurement errors, the standard deviation error and the mean bias error of the measurement. For the deformation measurement, the real-time measurement is very important for control and monitoring. For example, the real-time control of satellite formation and the deflection monitoring of the bridges. Because the deflection is very important, is a very safety parameter for the bridge. So it's better to realize the real-time monitoring. And the second part is real-time three-dimensional deformation sensing. So to realize the real-time three-dimensional sensing, so the core algorithm is the subset matching algorithm. We can use the efficient inverse convolutional Gauss-Newton algorithm. This algorithm is very popular in these years because it has a very fast computational speed, and there are many parameters during the iteration. Many parameters remain the same, so we can pre-compute these parameters before calculation. And this algorithm is an interactive algorithm. So during each interaction, we need to compute the incremental deformation vector, and because many parameters can be pre-computed, so the computational efficiency can be very high, and the calculation accuracy of the algorithm is also very high compared to some other algorithms. As an interactive algorithm, the initial guess is very important. Normally, we can estimate the translation before and after deformation, but it can not work for rotation measurements and some large deformation measurement. If the first order shape function is used as the equation in the screen, we know that if we just estimate the translation u and v, it is not enough because we have some other parameters. If these parameters are large enough, even if we have the complete correct translation, it cannot convert to the correct values. So the initial guess should include both translation and deformation. To do this, we use the deformation transfer thing. Before calculation, we should choose some seed points, and for the seed points, we use a temporal deformation transfer to calculate the inertial guess. And the simplest way is to use the current deformation as the initial guess for the next frame deformation, and or some other methods can also be used. And for the special deformation transfer, we can use the deformation of the calculated points to predict or to transfer the deformation to the neighboring points, and one by one. So for this deformation transfer thing, we can estimate both the translation and the deformation as the initial guess. So it can overcome some applications of rotation and large deformation. Because sometimes the temporal deformation transfer may fail, so we can choose multiple points to do the temporal deformation transfer, and then after these seed points are calculated, we can use these seed points to do the special deformation transfer. In this way, the real-time 3D deformation can be used for both small deformation and rotation measurements and large deformation measurements. Then for the temporal and serial matching, we choose the first choose the left camera image in time in the reference stage, and as the reference image for all the matching. So at first, if we capture the reference images, so we match the left camera image with the right camera image, and after that we start the real-time measurements. So in the next time, we need to correlate the left camera image with the left camera image at the next time, and for the right image, we directly use the same left camera image to match with the right camera image. So the deformation between the left camera image and the right camera image at the reference stage can also be used to do the temporal transfer. And actually, the transfer is the perspective transformation, and then deformation can be transferred for some other times. In this way, the computational efficiency can be improved, and then we use the CPU to accelerate the computation, and the parallel computation can be used. And before calculation, we build a queen queue and a mask for the computed points, and we create multiple seed points and insert these seed points into the queue and label these seed points in the mask. And we trigger the threads. For each thread, he can get an uncalculated point from the queen queue. So if it is original created seed point, it can calculate it uses the method A. And if it is other points, some points other than the seed points, it can be calculated in the method B. So the difference between the method A and the method B is that for the seed points, we use the temporal deformation transfer, and for the points other than seed points, we use the spatial deformation transfer thing. The other steps are the same. We need to match the matching with the left camera image, matching with the right camera image, and if these two matching are successful, we do the 3D reconstruction and the displacement calculation. So the CPU-based parallel computation can help to accelerate the computation. And moreover, we to ensure that the computational efficiency is guaranteed. To ensure that it is fast enough, we also use the digital speckle patterns. We transfer the optimized speckle patterns to the surfaces. So the speckle pattern has very good gray intensity and distribution. So even if we choose a very small subset size, we can also have very good results, because the subset size affects the computational efficiency very much. So in this way, we can realize the real-time three-dimensional deformation measurement, and actually it's just to calculate the deformation in a very fast way, and it's not the real time in real sense. So it is calculated in a very fast way, and we can, for the field measurement, we can realize the 10 frames real-time measurement with 6,000 points, and it can have many applications. So for the two-camera system, the hardware is very simple. We have two cameras, left and right cameras, and this the light, and this is the software we developed for the real-time measurement, and the software is also very simple. It have only some simple functions such as camera calibration and the real-time calculation. There's another hardware we developed for some special applications in the large engineering structures, and this is the corresponding software. So because we want to use the real-time measurements in the large engineering structures, so how to use these optical methods for the deformation of large engineering structures. The first way is a very direct way. If we can make the optical device very small and compact, so we can just use it as a strain gauge. The strain gauge can be attached onto the structures, larger engineering structures. If we can also make the optical device very small, we can also put it on the structure and use it for local deformation measurement. It is the very simple way, and it can solve some problems, because the strain gauge can, although the strain gauge can be used for deformation measurements, it cannot be used for high temperature deformation measurement. So for the optical strain gauge, it can be used for high temperature strain measurements in many applications. And if we want to measure the global deformation of the whole engineering structures, we need to use many cameras. For example, for the structure with the diameter of 6 meters, we needed to use 18 cameras, and for this structure, we even needed to use 40 cameras. So use these cameras, we can measure the global deformation of the whole structures. And there are still remaining some problems to be solved. The first is the calibration of the shear vision system for large field of view, because it will be used for large engineering structures. How to calibrate the system? So we also propose some methods to calibrate the intrinsic parameters of cameras. We use we find that in the laboratory we have many big, very large walls. So we paste some coded points on the walls, and we reconstruct these coded points based on the close range photogrammetry. And then the wall can be used as the calibration board directly. And instead of we change the position of calibration board, we can change the position of the camera. So the wall is steady, and we can move the cameras to take pictures from different views, and then it can be used for intrinsic parameters calibration, and the reprojection error can even reach 0.03 pixels. So how to with the calibrated intrinsic parameters, so we can install the cameras to around the large engineering structures. Then we need to calibrate the intrinsic parameters between these cameras. So we can use the bipolar constraint, and for a point, its projection to the two cameras, point P1 and P2. For the point P, these 3 points should be in the same plane. So we have the coplane equation to solve this problem. And for the intrinsic parameters, we have 6 parameters to be solved. And if we normalize the translation parameters to the last one, the TZ, we will have five parameters, and we still need scale information to calculate the TZ. So sometimes we use the scale bar to calculate the scale information. And with this optimization, the intrinsic parameters can be calculated, and in real time, because each frame, if we match the points, we can calculate the intrinsic between the two cameras. And because we use many cameras and many shear vision systems, we need to unificate this system into a global coordinate. So this is the first system, and this is another system. We need to unify these systems into a global coordinate. So we also use the close range photogrammetry. We reconstruct the points on the mirrored objects, and then the mirrored objects can help us to do the coordinate unification. Just as this point has been reconstructed, and this point some points can also be reconstructed by the shear vision system, and this part can be reconstructed by this shear vision system, and then we can calculate the rotation and translation vector between the camera coordinate system and the world coordinate system. Then this system these systems have a unique global coordinate system. And this is the software we developed. We integrate the close range photogrammetry methods and the shear vision method into the same software, and we call it the camera network software. And then we have this method, and we have this the hardware and the software. We can do the applications. So the first application is the optical strain gauge used for large engineering structures. For the large engineering structures, if the surface in the temperature of the surface is very high, the strain gauge cannot be used. So we can use the optical strain gauge. We install it in the inner surface of the high temperature surfaces,
then we use the water and air cooling to protect our cameras inside the system. Then we can to record the spectral images, and it can use to capture the local strain. This is the spectral images we capture at 300 degree, and this is 1000 degree. And we also have some accuracy verification experiments compared with the strain gauge, and the accuracy is good enough for this application. And another application is we use 2-camera system to do the real-time measurements, but we not to do the full field real-time measurement. We do the multi-points real-time measurements. So we put the spectral target in the field of view, and then we can track these targets, and we can realize the 16 frames with 15 points. This is a very interesting application because on the table they simulates the satellite formation, and they needed to realize the real-time control of this satellite model. And another application is we use the camera network system to measure a large cylinder structure. The diameter is 9.5 meters, so it is very large. We use 24 cameras. This is the hardware system. With this, we have 24 cameras, and this is we have 12 light source, and for each 2 camera we have a computer to calculate the deformation in real time. And so 42 cameras, we have 20 computer, and then this is in the experimental site, and we have 2 computers here. This all in real-time measurement, and because for the loading position, the real-time measurement is especially important, because in this presence, we need to know how the deformation and we need to control the loading. So it's very important. So the real-time measurement can help them to make the experiment, this experiment more successful, and they are very interested in our systems, and I think it's a very good application. And also we can use in some other large structures in the large shaking table test, and in our college, we have a large shaking table, and to shake the different buildings, and this is very important for the structures design, and to resistance to the earthquakes. And we also use our systems to do the real-time measurements, and we also put some encoded points for the coordinate unification, and this speckle we transfer some speckles on the structures for deformation measurement, and the height of this structure is 10 meters. And in this experiment, we can use the optical method, deformation method, to replace the traditional strain gauge and some other measurement methods, the traditional measurement methods, and they think that
the optical deformation methods have many advantages, and we don't need we can set up these cameras around the shaking table, and we use it for many years, and it can save a lot of time, and a lot of money. And another application is the crack monitoring of large concrete beams. We use many many cameras, and each camera we can do the real-time measurement. For each shear vision system, we use several shear vision systems to do the deformation measurement of very large concrete beams. And for the concrete design, the crack is a very important parameter. So they want to monitor the cracks in real time, and we can calculate the strain. Actually, it is just not the real strain for the crack. It is the crack may induce some puddle strain around the crack, so it can be used directly for the crack monitoring. And the real-time measurements can help them to control the loading, and can helps them a lot. So we build these systems and realize the real-time three-dimensional deformation measurements, and we have some applications in different fields, and it's in these fields the methods can be very useful and have some contributions. Thank you for your attention.
Thank you, Dr. Shaw. Your talk is very good. Are there any questions? No. I have a question. Do you measure the strain of the inner surface of the satellite? What is the temperature around the camera?
Okay. For this application, the temperature around the system is about less than 1,000 degrees, but about 700 to 800 degrees. But we use the water and air cooling the system. Then the temperature can be reduced to less than 16 degrees.
So the speckle pattern you fabricate on the surface is also can resist high temperature?
Yeah. The speckle pattern is fabricated by the methods developed in the Professor Xie's group in Tsinghua University.
Okay, thank you. So if there is no more question, we have to close this session. Thank you again, Dr. Shaw.
Thank you.